today it's a pleasure to listen to Alicia Kollár, who is in University of Maryland. She will speak about physics, about the circuit quantum electrodynamics lattices, synthetic quantum systems, online graphs. And as usual, if you want to ask questions, you should ask them in the microphone. So I think we have only one this week, but ask me for the microphone if you want to interrupt to ask a question. The floor is yours.
Okay. Thank you very much. Thank you very much for the invitation. I'm very excited to talk to you guys about the sort of the work that I've been doing. So most of what I'm going to talk about is joint work with Peter Sarnak at the interface between math and physics. I am an experimental physicist by training, and I have tried to remove as much physics jargon as I can from this talk. But if I've failed and I'm not being clear, then I really, please stop me and ask questions. I can clarify things, but I may be using the wrong words. Okay, so I want to start by telling you basically how we got interested in these problems and then the things that we've managed to do. And so I'm an experimental physicist, and so why am I giving a talk on spectral graph theory? Well, so the reason is because that my lab is interested in making synthetic quantum systems. And so why would we want to do this? Well, the reason is because that almost everything that you touch in everyday life is made of the same sets of ingredients. All of the physical materials that you touch contain sort of the following three things. They have a periodic arrangement of ionic cores of atoms. You have electrons that are mobile and can move between the sites formed by those ions. And then you have Coulomb interactions between those electrons. This seems like a very simple set of ingredients, but it leads to basically everything that we know. So it leads to metals that you would use for construction or for electronics. So rigid metals and soft metals. It leads to insulators like the jacket on these wires that keeps them from shorting, but also ceramics in the coffee cup. These are all coming from the same set of ingredients. And you can also get much more unusual phenomena like superconductors. And so the entire field of condensed matter physics is really trying to understand how it is you can go from this very simple, very common set of ingredients to such a wide variety of phenomena. And the traditional approach is you find a material that you're interested in and you start doing measurements on that material. But you could also think about doing this the other way around, where instead of doing experiments on the material, you want to try to do experiments on these ingredients. You combine them in different ways and try to see what sort of phenomena arise. And so you get to this idea of sort of a generalized material. It's something that consists of a periodic arrangement of lattice sites. You need some form of itinerant particle, and you need particle-particle interactions. And in a traditional physical material, these lattice sites are atomic nuclei, and these itinerant and interacting particles are electrons. But at an abstract level, they don't need to be that. If you can start to make this out of a different set of ingredients, then this allows you to perform a different set of measurements than are naturally available in solid-state systems. And so this is the broad theme of the field that I work in. It's sometimes called quantum simulation or quantum emulation, but really the idea is that we want to look at this generalized model using different implementations that allow us to make different kinds of systems and different kinds of measurements. Okay, and so with that context, what I'm going to tell you about today is the particular hardware platform that I work in. This turns out to have a lot of connections to graph theory, in particular line graphs, and I'll show you why this part of graph theory is really the right way to think about these systems. And then I will tell you about some examples where understanding the mathematical connections has really allowed us to make new progress in this hardware. And then in the latter part of my talk, I really want to highlight the fact that somehow this has really led to a lot of cross-pollination between math and physics. So known math results leading to us understanding our physics better, and physics methods being applied to graph theory problems. We've really been able to make a lot of progress by uniting these. And then I hope in the last few minutes of the talk to show you what actual experimental data looks like when we go and try to build these systems. And please feel free to interject and stop me at any time. Okay. So first I want to introduce what's the hardware that we're actually using. So my group works in a hardware platform called superconducting circuits, or circuit QED. And what this means is that we use the lithography or patterning techniques that have been developed for semiconductor devices, so the kinds of things that make the chips in your phone. Those sorts of methods, we apply them not to silicon, but to these superconducting films, which allow us to make very low loss, very highly controlled structures. And we have sort of two main ingredients that we can combine. The first is something that's called a resonator or a cavity. This is what our favorite one looks like. You should think of this as a two-dimensional version of a coaxial cable. So if any of you have ever played around with old analog audio systems, you have cables that have a central conductor with two ground planes on either side, and they form a guided mode for electromagnetic waves. And so this is basically what we're looking at. But if you break the structure and you cut parts of the center pin, then you ruin the guiding and you cause a very strong reflection. And so you have a very strongly confined wave propagating in this structure. This is a cartoon version. This is what they look like in practice more. So this whole structure here is about 8 millimeters in arc length, and you get to this point here where there's a gap and the microwaves reflect back. And so this is a microwave resonator. This is one of the workhorses of the field. Mathematically, this is really a harmonic oscillator. It's a harmonic oscillator in some slightly unconventional coordinates, which we call charge and flux, rather than position and momentum, but it's a mass on a spring and it's a harmonic oscillator. And we use this because it can be made very controllably. And actually the fact that it has these meanders in it is going to be really key to what we talk about next. And so this is a very well-controlled linear system that we can make. In order to make something interesting, however, we need some nonlinearity. And so for that, we use superconducting qubits. And the current forerunner in this field is the transmon qubit. This is a sketch of the circuit for it. It's a capacitor in parallel with this object here, which is called the Josephson junction. So the physics of that is not something that I want to get into, but there's a relatively simple math description of this, which is that this object is an anharmonic oscillator. So instead of charge squared, flux squared, we have a cosine phi term here, which gives it a nonlinearity. And so you can think of this as a nonlinear oscillator, or you can actually think of it as a particle in a cosinusoidal well, because this cosine phi term is the largest compared to this much smaller charge squared term. And so this is the basic idea of a transmon qubit. It's this anharmonic oscillator. And because of the structure of quantum mechanics, you have eigenstates or eigenvectors of this Hamiltonian only at certain energies. And the hallmark of the harmonic oscillator is that the eigenvectors are evenly spaced in energy. The eigenvalues are evenly spaced. Because of this cosine phi term, the eigenvalues are not evenly spaced, and so we can isolate individual components of this circuit. And this gives us a nonlinear object, which we can also sort of think of as an analog of a small magnet. And so it's actually fairly easy to combine these two elements together, because what you can do is just actually pattern the transmon qubit itself inside your cavity. And so this is a sketch of what this looks like. So here we have a zoom in of the resonator, and the transmon consists of a capacitor formed by these two pieces of metal, and the Josephson junction, which is the nonlinear inductor portion, is in this little green line, and we're not going to get into how that actually arises. In practice, it looks a little bit more like this. So this is the design that we actually have in our device. The capacitor is now this yellow digitated object and the blue one. And this is just to give you a little bit of a flavor of what these actually look like. In the end, though, what you should think of this as is we have the ability to pattern harmonic oscillators where we control the frequency, and to pattern these anharmonic oscillators and combine them together. This is the architecture that's used for superconducting quantum computing. And in that case, what people do is you use the transmon to store quantum information, and you use the resonator to bring control and readout signals in and out. And so you can think of this as sort of a photon-controlled magnet in that case. Or you can think of it as the transmon is an anharmonic oscillator, which allows you to add nonlinearity to your resonator. And so my group is not focused on traditional quantum computing. Instead, we would like to understand what happens when you combine many of these systems, particularly in periodic arrays, and what is the new physics that you can have in that case. And so for us, a lattice is going to be something that looks like this. So this is a photograph of a device that was made at Princeton about 10 years ago now. So we've now zoomed out, and each of these wiggly lines here is one of these coplanar waveguide resonators. And they meet at these little junction points. And so if we zoom in, what's happening is the center pins of three of the resonators converge. And where they come close together, this allows a photon that is moving in this resonator to jump or hop in physics terms over to the next one. And so we can think of this as an artificial material for microwave photons. They are predominantly confined onto one of these resonator lattice sites, and then they can move according to the network onto the others. And so this is the physics description for the energy of the system. And so you can think of this A as a complex vector that describes the state of the photons on all of the resonators. And this has two pieces. This is the resonant frequency of the resonators. So this piece is a multiple of the identity, and so we're typically going to leave it off. And this piece is describing the ability of a photon on one site to be converted into a photon on the other site. So this is the hopping. And this is described by a graph adjacency matrix. And so if we want to understand the physics and the energetics of the system, we really just need to understand this particular graph adjacency matrix. And so there's a very intimate connection between the physics of these things and graph theory. The way the physics works out, this coefficient here is negative. And that means that the constant function is going to be at high energy rather than at low energy. This is a bit counterintuitive from the physics point of view. Another thing that I want to point out, which is a bit of an important distinction on the math side, is that the key operator here is not the graph Laplacian, but the adjacency matrix. So for regular graphs, that doesn't change anything, but for irregular graphs, that can make a serious difference. And so it's just something to keep in the back of your mind, that we're really going to be talking about the adjacency matrices here and not the graph Laplacians. Okay, and so why do we like this platform? So it turns out there are two very unique things about it that allow us to make systems that wouldn't otherwise be possible. And so the first thing is that the lattice site is in a certain sense deformable. And so what do I mean by that? So this is a close-up of one of our lattice sites, and I want to look at what are the key properties that it has. So the first is that the frequency depends only on this total arc length. You're looking at how long does it take a photon to go to one end, bounce, and come back, that's what's going to set the resonant frequency. And the second is that the coupling comes from the endpoints, and it's a very simple function of the endpoints. If you think about how electrons on two atoms couple, then you have some electronic distribution centered about the ionic core. And when you move the ionic cores around, that changes how much these electronic distributions overlap and how much the electrons can move. Here you have a much simpler scenario where just the end matters. Nothing about the middle, what's going on in here, is going to determine whether a photon can move from one resonator to the other. And because it is a waveguide, it's like a cable. You can twist it up and make it smaller, and it will still have the same properties. And so that means that we can make structures that look like this. And you and I are looking at this in the optical frequency range, and these three look completely different to us. But microwave photons that propagate in the device can't tell the difference between these three structures. They just see a resonator with the same frequency and hoppings on the end. And so that means that you can make a lattice site sort of fit in a very different amount of space. These are shaped very differently, and the end-to-end distances are quite different. And so you have, what you've got here is graph-like flexibility in the connectivity. When you make a lattice out of actual atoms, if you change the distances between the nodes, you change the connectivity. What you're really changing is the weighting of the edges when you do that. Whereas here, you have an ability to change the shape without changing anything about the connectivity. And that's going to be incredibly crucial for what I'm going to talk about. And this is why we discovered that the right way to think about these systems is not so much in terms of traditional solid state physics, but in terms of graph theory. The other thing that turns out to be really important is that this is a graph not of points, but a graph of lines. And so if you come and look at the device and you try to see what was the lattice that was acting here, almost everyone, including myself when I started in this project, will look at this honeycomb pattern and think, this is a honeycomb lattice. But this isn't correct, because what I have implicitly done here is put the nodes on the coupling elements and the edges on the resonators. So this is not going to describe the physics of particles moving on this lattice. Instead, we need this graph here, where the nodes are on the resonators and the edges indicate whether those two edges share an endpoint. So we need the vertices on the resonators. And so what that means is that we are going to be looking at line graphs. So for hardware reasons, everything that we do is going to be built from something that is honeycomb-like, but the effective physics is always going to be on the line graph of this underlying object. And it turns out that line graphs are extremely special, and that mathematicians knew all about this, and physicists were in blissful ignorance, is not the right word, just ignorance of the special properties. And so we need to keep in mind that this thing is a line graph. Mathematically, it turns out to be very, very convenient to keep the underlying root graph around. Historically, I called it a layout graph before I knew what a root graph was. And so I will keep mentioning both of these things. The line graph is the final object that matters, but mathematically, it's much simpler eventually to talk in terms of the root graph. Okay, so that was my sort of whirlwind introduction to the hardware, and hopefully that gives you an idea of why we really want to look at graph theory for how to think about these systems, because we have flexibility in the connectivity that's not natural in other lattice systems, and all of the lattices that we make are going to be line graphs. And so basically what we started out to do with Peter was to try to understand what this would allow you to realize in the lab. And so in the next part of my talk, I want to show you two examples of very, very unique lattices or graph spectra that we were able to realize by understanding the effect of these two properties. And so the first idea we had was that, well, we have this graph-like flexibility that you can move things around without changing the connectivity. And so this gives us the potential to realize a lattice that is not actually in flat space, even though eventually we have to make a device on a flat two-dimensional substrate. And so we were intrigued by the idea of making something curved because, for example, general relativity tells us that curvature is a natural thing, but nobody has a lab in a space where there's a lot of curvature. And also the mathematics of hyperbolic graphs in particular is extremely rich. And so we set out to do this. And the way that I like to think about this, as a physicist, when you learn about lattices, you think a lot in terms of translation symmetries in 2 or 3D Euclidean space, and that doesn't work well. And so we start to think about this instead in terms of tiling rules. And so this is our sort of go-to example. This is the honeycomb. And the construction is you have hexagons, 3 of which share a corner. And if you change the tile, then you get something that's native, for example, on the surface of a sphere. So if you use 3 pentagons instead of 3 hexagons, and I think as this audience all probably knows, this is natively a spherical object, and so you cannot draw it on a flat 2D surface without distortion. And so this is my cartoon version of a half soccer ball, where when you flatten it out, you have to stretch things out on the edges. And this is just unavoidable. The hyperbolic case is the opposite, where instead of having too much space, you have too little space and you have to compress. And so this is the situation, right? That if you want to make a periodic tiling of a non-flat space on a flat object, you have to start changing the distances. There's no isometric embedding. And so what you need is a realization that doesn't care that there isn't an isometric embedding, because if you can preserve the Hamiltonian, which sets all the energies, it doesn't matter that the spatial structure is messed up. And that's the key that this circuit QED implementation allows us to do. And so these are 2 cartoon pictures. The spherical example is a little bit easier to see. So clearly the distances are all screwy, but what really matters is that you preserve the connectivity and that you preserve that term out front that was supposed to be proportional to the identity, so that you keep the frequency of all of the resonators the same. And so if we just use the same coupler at every point, it's sort of automatic that you preserve the connectivity and the hopping. The thing that's actually a little bit challenging is to make sure that the frequency of every resonator remains the same, and you do that by changing the shape. And so if you look in here near the middle, we have resonators with a large meander. And if you look here on the side where the distances are longer, we can put in a smaller meander. And so this allows you to have the same arc length of resonator, even though the end-to-end distance is changing. And so it's a natural way to think about taking this curved space tiling and producing its Hamiltonian or its adjacency matrix naturally on a 2D substrate. And so this is what that actually looks like in practice now. And so this is a device that was made at Princeton when I was a postdoc. And so it's a niobium superconductor on a sapphire substrate. It's about a 25 by 25 millimeter chip. And what it's realizing is the line graph of a hyperbolic honeycomb. And so this is a version of the honeycomb where you have a 7-sided polygon, a heptagon instead of a hexagon. And so this cartoon is in one-to-one correspondence with the device. And so you see this, the dark blue edges here are the resonators, and the light blue is showing you the line graph effective model that you actually get. And so in the center here, there are 7 resonators. Here are 7. This is another loop of 7 corresponding to this set, here's another loop of 7 going out there. And so we have this small flake of a hyperbolic lattice. It operates at 16 gigahertz, and we have these additional input and output ports that allow us to do a transmission measure.
Sorry.
And so here's the
so I have a small question. Can you comment again on the size of the device? Because I see it's small, but it's not super small either. So can you comment on the choice of the size?
So the choice of the size is actually set by some annoying hardware constraints. And so these resonators are 8 millimeters long, and that means that the eigenstates that we're looking for happen to be at 16 gigahertz. Below 8 gigahertz is comfortable, and above 20 gigahertz is sort of impossible. And so we can't make the resonators any smaller, and so this is about the smallest that we can make this. So for us, this is a large device, but not unusually large.
Okay.
If we use other types of resonators, we may be able to make it smaller. So there's lots of different ways to make resonators in this field, and so the question is, what are you most worried about? And so you can often change your approach depending on what you want.
Okay, so so it depends. So if you made the device larger, you wouldn't be able to test anything interesting, or what would be the problem?
It gets harder and harder to manage that the modes of the lattice are actually the only modes in the device. And so these are sort of annoying experimental technicalities. In this case, a lot of the problem is that you would like to make the graph itself bigger, but it's growing exponentially. And so you're sort of more limited by how much you can change the size.
Okay.
And so this is a hard one to do.
Okay,
it can be done, but it's a hard one. And so now maybe
sorry, there is another question in the audience.
Okay, perfect.
Yeah, hello. What is the width of the resonator? Not the length, but the width. Is it like a tenth of a millimeter? Or?
It is about 37 microns.
37 microns. Okay. Okay. And I have another question. I mean, here, are there any Josephson junctions in your setup here, or is it?
No. So this is junction free. Okay. So this is really basically to prove that this very nice little story that I told you of, I just changed the shape and it doesn't change the frequency. Yes. That the engineering is actually good enough to do that. This was a non-trivial task to actually make that work.
Okay. And are you at a very low temperature? Does it have to be superconducting?
Yes. Okay. So this data was taken at 15 millikelvin.
Okay. And the waves, I mean, when you say they are microwave resonators, are you the Hamiltonians you show? So are you really looking at the phase of the photons? So you really do you have to use quantum mechanics to describe the system, or do you just use classical wave mechanics? Because I know people who do microwave resonators at room temperature, but they're not using any quantum description. So
yes, and so because there are no Josephson junctions, this is a linear harmonic oscillator, and so essentially I don't need quantum mechanics. Wave mechanics is plenty. I'm not seeing the quantization here yet.
Okay, so you're propagating classical microwaves in some sense, or you're trying to what you measure here on your transmission, you're propagating classical microwaves. Okay, all right. Okay, thank you.
Yes. if we looked very carefully, we would see that these are so low amplitude that you might start to see the fact that it's not a perfect sine or cosine. But particularly for this data, we were going in at high power to get as much signal as possible. And so, but in the experiments that I will show you at the end of the talk, there are Josephson junctions, and now you can see the quantum nature of things. Yes, anyway, so I think the upshot of this particular plot for this audience is that being an experimental physicist is messy. There's a forest of peaks here that corresponds to different modes of the lattice. The idea being that we send in microwaves on this side, and if there is a mode at that frequency, then we'll get microwaves out the far side. But this device also has some disorder in it. There's variations in the device parameters because it's actually experimental. And so that means we can't model it perfectly. And so we have, in red here, we have an ensemble of theory curves where I put in a few different disorder realizations, and it mostly accounts for the difference between the experimental transmission and the theory. We understand these differences better now, but this is the first version showing that things basically worked out. This was sort of the proof of principle experiment that the microwave engineering could be done. Okay. And so now I want to this is the motivating story that we can make these kinds of things in the lab. And so now I want to transition to thinking about how should we understand these things and what can we do with them? And so as a physicist, when given a lattice, what I want to do is calculate a band structure. And so this is an example of a band structure for the Kagome lattice. And so what the band structure is if you have a translation invariant lattice, then you can use Fourier analysis to basically classify the eigenstates based on how much the wave function or the phase changes when you go from one unit cell or fundamental domain to the next. And so when we have a structure like this, then we always want to use the momentum to classify the states. And so these bands here are the eigenenergies as a function of momentum, and this kind of system naturally gives you surfaces like this if it's a Euclidean lattice. But as we all know, hyperbolic geometry is non-commutative, and so we can't do something like this. Instead, we have to use more general techniques. So either graph theoretic methods or finite size numerics. We can't make curves like this. And so when you start doing the numerics for this particular hyperbolic lattice, this is what you get. This is a sort of strange plot. And so what we're doing is we are just computing all the eigenvalues of the adjacency matrix of this lattice for different sizes. Starting from a small one and then adding one shell of plaquettes and going out. And then when you do this numerical diagonalization, it just spits out a list of eigenvalues in order. And this region is sort of a mess, but there's something remarkable going on down here. So one thing that you'll notice is there's a huge degeneracy. So about 20% of the eigenvalues are all -2. So this is a very unusual thing to find in a lattice system. It's also very, very intriguing to a physicist because what we're solving here is the non-interacting problem. And so there's a massive degeneracy in the non-interacting problem. And what experience in physics has shown is that if you have this kind of a large degeneracy and then you add interactions, the interactions dominate the physics and you can get very, very dramatically different behavior. So this is extremely intriguing. The other thing that's very, very unusual is that this, I'm going to call it a flat band. It's a bit of an abuse of terminology, but I'm going to go with it, is actually separated from all of the other states. So there is a gap in the spectrum between these degenerate eigenvalues and anything that comes after. And this is what you get for moderate sizes. If you really make your laptop cry and go to larger and larger sizes, you can compute a density of states. and you see the corresponding gap in the density of states here and here. And so this was actually the reason that we chose this particular lattice to implement. We were very, very intrigued by this flat band that was all by itself. And so we were hoping to build up to a system where we could add Josephson junctions and start creating interactions in that band. Unfortunately, this gap is not particularly large compared to experimental uncertainties. And so one of the things that became really important was to understand where this gap was coming from, and could we make it bigger? Could we get a much better separation between the unconventional eigenstates in the flat band and sort of the normal states in the rest of the spectrum? And it turns out that the key to understanding this is to realize that we're dealing with a line graph. And so now I want to loop back and look a little bit more carefully at what does it mean to have a line graph. So this is the first pair of graph and line graph lattices that any physicist has ever seen. The honeycomb lattice and its line graph. This is the two of them on top of each other. I apologize, the color scheme reversed when I put them on top of each other. And so to go to the line graph, you take the original graph and you put new sites corresponding to every edge, and you connect those sites if the edges are incident on one another. So that gets you from here to here. And this is a very general graph operation, right? So this is the most famous physics example. This is the one that we just talked about, but you can do this in general. And so what we started to do was look at not these two examples, which are closely related, but these two examples, because they are Euclidean lattices where we can launch the full suite of tools from solid state physics and solve everything about the eigenstates. And so if we look at these, all right, I'm going to try to speed up a little bit so we can talk about more stuff. So this lattice, the honeycomb and its line graph is called the Kagome lattice. These are the bands for the honeycomb and Kagome. This is the square lattice. Its line graph looks like this. There's no lattice site here. These are just extra edges. And so when we look at these surfaces, we start to see a pattern. So both of the line graphs have this orange flat band here. So this is a massive set of degenerate eigenstates at -2. And then interestingly, these bands and these bands look exactly the same. And this one and this one. And what it turns out is that this is a fact that was known to mathematicians for decades, and physicists had no idea that this is a statement about the line graph of regular graphs. And this is one of the key places where Peter was able to help us connect to the graph theory literature, and we started to really see these things coming together. And so let's look at what this correspondence actually is. And so there's two operators that we would like to relate. So one is the Hamiltonian on the underlying graph, and one is the effective model on the line graph. And the key to relating these is to use the incidence operator, which maps you from the graph to the line graph, and the incidence operator maps a node to the edges that are connected to it. And so the key is that if you take M transpose M and you multiply in this order, then you get the Hamiltonian on the starting graph plus a diagonal matrix of the coordination numbers. And if you multiply in the other order, you get the effective model plus twice the identity. And so if it's a regular graph, then this is also a multiple of the identity, and that allows you to relate the spectra of these two. As a physicist, I would say that these are almost equal, except for the fact that one operator is significantly larger in dimension than the other. But what it really means is that when you go from a graph to...
I have a question about the boundary. Peter always talked about regular graphs, but here you have a boundary, and the boundary points are not regular. So what do you do with them? So we're going to sort of talk about two different cases. So one is
what the typical solution that a physicist does is you compute with periodic boundary conditions, and this gives you the ideal solution.
Mm-hmm.
And then you ask sort of what changes when you add a boundary. And so you can add some edge states, but you can't really get rid of anything that was in the spectrum beforehand. So anywhere where there was a macroscopic density of states before you add walls, you can't really get rid of, at least in the Euclidean case. And so we've looked at it numerically sort of both ways, but
it
in
was
general,
for
we find that it's...
I guess in the hyperbolic case, the boundary really plays an important role, and
it does.
It does.
It does.
Okay.
And so let me come back to this point in a slide or so.
Okay.
I think I will be able to make a better statement.
Excuse me, I also have another question. Yeah. Can I interrupt you? Sorry. You speak of band structure because this band structure, it works when there is a Euclidean translation invariance, okay, so some periodicity. Mm-hmm. So, but are you saying that this works, that this correspondence works also for graphs which are not periodic or which don't have this periodicity?
Yes.
Okay. And you have this extra.
It's really the underlying correspondence is one eigenvector and one eigenvalue at a time. Okay. You can map the eigenvectors one by one and the eigenvalues one by one, and it works. And so it also maps the band structures. And so what my understanding is that this is a statement that was very well known in finite graphs. I think Peter found it in a textbook, chapter 1. The corresponding statement for infinite graphs was, I think, proved in the early 2000s. And so what was going on is that this statement has profound consequences for these infinite periodic graphs, but it was sort of proved in a very, very different context, and sort of nobody had any idea that these things were related, at least on the physics side. And so what it's saying is that you have, on a line graph, you have two types of eigenvalues. One that comes from just the eigenvalues on your original graph shifted up, and these flat bands that are coming from the kernel of MM transpose. And so if we go back and look at our list of graphs, we can get a mapping like this. And so now I have put the underlying graph, the line graph, and I have sketched below the support of the density of states for all of these cases. And then what I've shown here in red and yellow is actually an eigenstate from the flat band. And so in each case, what happens to the density of states, if you did this without boundary, is the density of states moves over, and then you add a flat band. These graphs are bipartite, and so the flat band comes and it touches the rest. These graphs are hyperbolic, and so their eigenspectrum doesn't go quite all the way to 3 and -3. And sort of, as Nalini pointed out, the hyperbolic case, the boundary is very significant. And so in this case, when you cut it, the gap actually closes, this gap down here. But it turns out that in this case, when you cut it, the gap doesn't close. This doesn't close all the way. And that turns out to be because this is a non-bipartite example. And so it was a little bit of an accidental discovery, but there are two things going on. One is the expander gap, and one is due to the non-bipartiteness. And the expander gap part goes away, but the non-bipartite gap does not. And so that's what leads to this example being gapped. And that was sort of the fundamental understanding, that you want to make this as non-bipartite as you can to push this lowest eigenvalue as high as possible, and that's how you make a large gap structure. Okay, so I think I'm running late, and so maybe I will sort of skip to the punchline. But the next thing that Peter and I realized was we could use again, graph theory, in particular line graphs, to make an example with a very high least eigenvalue, because line graphs actually have the largest possible least eigenvalue. And so what we needed to create for the hardware was a 3 regular line graph. And you can do that by starting from a 3 regular graph, adding sites in the middle of every edge, and then taking a line graph again. And so if we use this as the basis for our hardware, this is the effective model, and it gives a structure like this. And so there's a flat band at -2, a gap of 1 hopping, so the 1 unit of the connectivity, and then comes the next states. And what we were able to prove is that this is the largest possible gap that you can get in this area, because line graphs have the largest least eigenvalue. And so this was sort of the first big math result that we got. Okay, and so now I want to keep going and show you where this led. And so the first thing that we started to think about was, well, there's this, we were able to prove that this gap at the bottom between -2 and -1 was realizable, and that that's the largest possible gap that you could have. And interestingly, it's realizable in planar graphs. This is not entirely normal for graph theory, right? If you look at the expander gap at the top, that has very, very strong constraints that planar graphs aren't going to do this. And so it led to 2 natural questions. Can we get even larger gaps somewhere else in the spectrum? And when does it matter if something is planar or not planar? Because we have sort of these 2 examples, the line graph gap at the bottom and the expander gap at the top, where the dependence on planarity is very, very, very different. And so we started looking around, and we were able to prove a couple of theorems. And so the first is that no large 3 regular graph can have a gap larger than 2. And in fact, we found 2 example graphs that have this gap. And so this is the first one. So it's a sort of one-dimensional periodicity. It has a gap between -2 and 0. And this is the second one, which has a gap between -1 and 1. And we conjecture that these are basically the only graphs that have this. You know, anything that has this gap is somehow a variant on these 2. We weren't able to prove it, but that's the conjecture. One thing that's very interesting and has turned out to be incredibly fruitful again is that we derived this graph from the cube. But if I redraw it like this, what you start to see is that this is related to the honeycomb. So this is actually the honeycomb rolled up into a very tight cylinder. And remarkably, these are objects that occur in nature. They're called carbon nanotubes. So carbon naturally makes a honeycomb lattice, and it can form these tubular structures. And this is basically the smallest non-trivial nanotube. I think the diameter of this one is so small that it doesn't occur in nature all that much, but the slightly larger cousins do. And so that was already a remarkable connection. This object has been studied in physics before. And so I think one of the really interesting things, at least for me, about this project was that the key was really to combine a mathematical viewpoint that was completely new to me with solid state methods for band structure calculation. And the reason that we were able to do this result is that we adopted the notion of abelian covers for generating lattices. And this audience probably is very familiar with this, but for physicists, this was a very alien concept. So the idea is you start with a finite graph, and then you want to produce a lattice by tiling that graph. And so you cut one edge and reattach it to the next neighbor, and you can create a periodic graph from a small finite one. This is actually one of the maximal gap examples on the previous slide. And the thing that's really important or really, really helpful about this particular picture is that small graphs and their spectra are tabulated. And it turns out that the eigenvalues of the small graph are the zero momentum eigenvalues of the extended object. And so you already know some information about where the spectrum of the extended object will be. And it turns out to be very simple to use block theory methods to numerically compute the spectrum of the extended lattice. And so, there's a way to systematically generate lattices from a finite graph. And so what this lets you do is a numerical search. You pick out a finite graph and you just start unpeeling it into different lattices. You can do a quick calculation of what the spectrum is. And if you're interested in lattices with a gap at a certain energy, then you just look for starting graphs whose eigenvalues are far from that energy. And so it's like having a periodic table of unit cells from which you can then systematically search for good examples. And this is how we found those two maximal gap ones. I think they're both, in fact, abelian covers of the cube. And this also let us prove a second theorem that says all points in -3, 3 can be gapped by large 3 regular planar graphs. And this was a combination of numerical search and this operation that we had invented for maximizing the line graph gap at the bottom. And so these are 4 planar graphs that we discovered just by numerical search. And this plot here is showing their gaps. And so, for example, these intervals in red are the gaps in the spectrum of this graph. These correspond to that one. And so that's in the way. So between these 4 seed graphs, you have gaps that cover the entire interval from -3 to 2√2. And then Peter was able to show with dynamical maps that if you apply subdivision and line graphs to these over and over again, you'll generate a gap at any point except right at 3, where it would be an expanded gap. And so this was really a combination of standard numerical methods in physics with this mathematical idea of how to generate lattices. And the reason that this was so different is that solid state physics comes from chemistry. And so if your point of view on how to generate a lattice is the chemistry of how atoms arrange, then this sort of abelian cover construction is extremely unnatural. But it turned out that for this problem, it was perfect. Okay, so I'm running very late, and so maybe I will skip this next section. But it turns out that we were able to use all of the codes and methods that I developed for this project with Peter to look at instead the spectra of certain quantum error correcting codes. And this involved looking at oriented versions of graphs instead of unoriented. So I will skip through that, but I want to talk about 2 things in the outlook very briefly in my last few minutes. And this part here is a joint work with Fan Wei and Peter Sarnak. And so the previous result that Peter and I had showed is that if you have a planar graph, you can get a gap anywhere except at 3, a planar 3 regular graph. But in order to do so, we had to let the size of the faces diverge. And so we asked sort of the next question, well, what happens if you don't allow that to happen? If you want this to really be a tiling with some basic set of tiles, can you still do that, and what are the constraints? And it turns out that these nanotube graphs are incredibly important in this context as well. And so nanotubes, as I said, are what happens when you take a ribbon in the honeycomb and you curl it up. And so this is the tube-like graph that you get from this fundamental domain. So let me just sort of skip to the punchline that we had this particular graph here. And when you make it infinite or periodic, it has a gap from -1 to 1. But it turns out you can make this planar by sort of pinching off the ends. And when you pinch off the ends, that gives you a couple of triangular faces, but it doesn't actually change this gap from -1 to 1. And so if you allow faces of at most 6 sides, it is still possible to realize this maximal gap, but you have to have triangles. And if you disallow triangles and you allow only hexagons and pentagons, then actually this nanotube is the thing that's going to give you the largest gap. And it's the single only example. So that's sort of interesting that as you do these constraints, you hop between different classes of nanotube. And this actually has interesting connections to chemistry, because this class of graphs, which are 3 regular with only hexagons and pentagons as faces, are called fullerenes. And the most famous fullerene is the carbon C60 Buckminster fullerene. This was the subject of a chemistry Nobel Prize. And there was actually a conjecture in numerical chemistry from the 90s about whether if you take a spherical fullerene like this and you take the size to infinity, do the gaps close? And so that's, we've been able to prove that those gaps do indeed close, and also that the only large fullerenes that will have gaps as the size goes to infinity are these nanotube-like fullerenes. So it should consist of a tube of honeycomb with end caps. And this example, the so-called 5-0 nanotube, is the dominating example that controls all of this behavior. Okay. If someone wants to ask me a question, I will go back, but I wanted to just end by showing a little bit of experimental data. And so in my lab, we are actually working on realizing this in hardware. And so what we wanted to do was realize this layout graph and this effective lattice now with qubits, so with the Josephson junctions. This was an example that was identified by Peter as having sort of all of the possible ingredients that you could get. So it has a gapped flat band, it has conventional bands with a quadratic extremum. It also has this linear band crossing, which is unusual. And so we set out to make it. And so now this is what the design for the device looks like. And so you see this rhombus chain structure snake through the device in an S-curve. It has these extra lines here. These are allowing us to bring in a bias magnetic field to control the qubits. And inside each resonator, we have something that you can't quite see here. But if we zoom in, actually, we're adding these qubits that I showed at the very beginning of the talk. And so we're patterning them into the lattice. This is now what the device actually looks like. It's the same size as the old one, so 25 by 25 millimeters. It's now made of tantalum instead of niobium, but that's a detail that doesn't really matter. And now we can start to do measurements. And so this is a measurement where I'm showing transmission through the device as a function of frequency. And so each peak here is indicating a mode of the lattice. But now the qubit is actually frequency tunable by magnetic flux. And so as I change the applied voltage, the frequency of the qubit is changing, and it comes and interacts with the modes. And that's what's producing these avoided crossings here. And this is now really starting to be quantum behavior. And so the qubit passes through. Here's another dramatic piece of data. And maybe I will just stop here, but this is a very nice piece of data showing a slightly different configuration. So in this configuration, this is the expected band structure. And so what I've plotted in this plot here is I've done a differential transmission measurement. And so I've taken a horizontal cut from the previous slide and where the qubit is far away, and then I subtract that from all the rows. And so whenever there's a change in transmission due to the presence of the qubit, then we get features in white, and we see there's 2 regions where those features are showing up. And these are in very nice qualitative agreement with the expected density of states for this particular lattice. And I think I'm running very long, so I will skip.
I think it's okay if you take a couple more minutes. You don't have to stop exactly.
In that case, I will show you a little bit more of this data. Okay, and so one thing that I have slightly hidden is that there are two modes of operation in this device. One where we have a symmetric standing wave in the resonator, and where we have an anti-symmetric. So this is data from the symmetric case that has this band structure that we've been talking about. And this is a sort of fun measurement because what we discovered this measurement entirely by accident. This is how experimental physics works. You're trying to measure one thing and it goes terribly, and sometimes you manage to measure something else. And so we were trying to calibrate our qubits, and we saw this forest of peaks appearing around 9 gigahertz. And so what was happening here is that we were checking the properties of a mode at 5 gigahertz and driving very hard up here at 10. And because the qubit is nonlinear, it gives a nonlinearity to the lattice modes. And so what's happening here, for example, is that we're driving one of the modes of the lattice here at 9.8 gigahertz. And when that becomes strongly populated, it's changing the mode at 5 gigahertz and producing a response. And so each one of these dips is indicating when we have driven one of the lattice modes at 10 gigahertz. This is actually a much cleaner measurement than transmission. There's fewer spurious signals. And at the time that we first took this data, we did not have in our laboratory an amplifier that would allow us to measure at 9 gigahertz. So we got signal from modes outside of our measurement band. And here we clearly see 1, 2, 3 groups of modes. And this is the corresponding density of states that you would expect. And so now we're very clearly seeing a cluster of modes corresponding to this flat band. The middle 3 bands are in this region. This band gap is here, and we see the highest modes. And since then, we went back and added another amplifier, and now we're able to take transmission. And so now what's happening is that the qubit is coming up to about here and turning back around and going through. And so in this plot, I have the direct transmission data, and here is the nonlinear spectroscopy data. And interestingly, if you just looked at the transmission data, it would be very, very easy to miss the flat band. There's not a lot of signal here. If you look very closely, things are going on. But this nonlinear spectroscopy actually, even though it was a complete accident, this turns out to be an incredibly good way for us to see where the bands and the band gaps are. It's much cleaner than this transmission data. Like, this is a band gap, but it's hard to tell from the transmission data. And up here at the top, actually, if we really zoom in, we can again see the lattice modes reacting. And in this case, the qubit doesn't even enter this frequency range. I think it tops out actually here. Anyway, so this is the device that is actually currently being measured in my lab, and we're really using it to understand how to measure these things. And when I talk to theorists, they find it very confusing that I say, oh, well, we're learning how to measure it. But that is really what is going on here. We're figuring out what are the right ways to probe and measure this system. And we've been able to produce this lattice with qubits and are currently looking at mostly the interaction between the qubits that is mediated by the lattice. And so with that, I'll wrap up. And so hopefully I've showed you an interesting story of how a hardware question of what can we do with these superconducting coplanar waveguide lattices turned into a series of math questions. and that really there's been a huge back and forth with graph theory results leading to fundamental changes in our understanding of the hardware, but also then being able to harness combined math and physics methods to solve actually both math and theoretical physics problems. This has answered questions in spectral graph theory, quantum error correcting codes, and incidentally, actually mathematical chemistry. So we've had a really good time exploring all of this, and I cannot stop without thanking the institutions that made this possible. So there have been a large variety of funding agencies that supported both my postdoc advisor where this work started and my group. And Peter has really just been instrumental in bridging the communication gap between math and physics and being able to understand where there was knowledge on each side of the fence that could be used. The fullerene stuff that I described at the end is joint work with Fenway. And I really cannot thank enough Matthias Fitzpatrick, who is the graduate student who was crazy enough to say, hell yes, I want to make hyperbolic lattices, let's do this. Because it was my idea, but I was new to that hardware platform. And so he was the person that actually made it possible to make that first device and open this door. Okay. And with that, I would like to thank you all for your attention.
Thank you for the talk. We have time for more questions if there are questions in the audience.
Yes. Yeah. Excuse me, you went very fast over the slide on error correcting codes, but is it the reason why you are interested in gaps in order to protect quantum information in some sense, or is it why you're searching for maximal possible gaps?
So that was actually an accident, but so the reason that I'm interested in gaps is that basically degenerate experiments are never perfect. And so this is a theory plot that says, that says there's a perfect flat band here. But when we make this an experiment, it's going to be a little bit fat. And so it'll get spread out. And so the statement that I really would like to be able to make is that these imperfections are small compared to some dominant energy scale. And so it's kind of a general principle in physics that you try to get a separation of energy scales. And so I don't know if that's a great explanation, but these energy gaps basically protect your eigenspaces. And so if you want to say that there's only this subspace that is relevant, then you need to have a large energy gap between the states in that subspace and other things that might be coming in. And so it cleans your problem and makes it smaller. And in the error correcting case, the gap is what would protect you from sort of accidental errors occurring. But it's sort of like gaps are protection as far as the physicist is concerned.
Okay, thank you.
Any other questions? I think I would like to hear a little more about the boundary problems for hyperbolic because if you have an infinite hyperbolic graph, but if you just take a finite piece of it, then yes, I think I'm still a bit how to say. Yeah, I don't really understand what you do with the boundary of these finite pieces of hyperbolic graphs.
Okay, so I have some old slides that may be useful. So this is sort of a series of these numerical diagonalizations for different lattices. So hexagon, heptagon, octagon, and nonagon. And so the first thing that you will notice is that there's no gap here. And so these are for the finite case. And so in the infinite case, the octagon has an expander gap on both sides because it's bipartite. The octagonal honeycomb is bipartite, and so there's a gap on the top and there's a gap on the bottom because it's symmetric. And so one of the results that we showed was that, so we know that when you take this graph and you cut it, the expander gap has to close because it becomes planar. And in the bipartite cases, that turns out to imply that this gap must also close. And so we see that in numerics here, and maybe this is maybe the slightly better slide. And so what we've done here is two calculations. So these plots are showing exact diagonalization for the problem with boundary. And then, so there's sort of two ways that you can try to get the spectrum of this thing with boundary. One is that you can just do the calculation with boundary. And the other is that we look at the underlying root graph without the boundary and find the least eigenvalue, which we can get fairly well from like Landshut numerical methods, even out to big sizes. And so we can compute from that where the least eigenvalue of the underlying honeycomb is. And then from that, find the region where the ideal spectrum must be contained. Does that make sense? And so this yellow region that's highlighted here are eigenvalues that we get by diagonalizing with boundary that we know should not be in the spectrum without boundary. And so what you can see is that, and so the gap, if you didn't have to cut it, would be between these blue bars. But when you cut it, these yellow states fill in. And in the bipartite case, they fill in completely. And this is basically because you can show that the gap down here is equivalent to the expander gap at the top, and if one closes, the other one has to. And one of the things that Peter was able to prove is that in these non-bipartite cases, the gap does not close, even with the boundary.
Okay.
I'm pretty sure that was in the paper. It's been a while. But there's a bound, I believe.
Okay.
Yeah, but it is one of the unclean things about this particular method.
I think what I'm...
This was the first kind of... Yeah.
I think what I was concerned about is that it's known that the density of state is of the finite approximation doesn't converge to the density, to the infinite density of state. It converges to something else. But here you're more interested in gaps, so it's not the same. Yeah, it's not the same question.
Yes. So that is definitely the case, and we see this in numerics. Like, for example, this is an example of one of the states that's in this yellow region. And as a physicist, I say, oh, that's a whispering gallery mode. So this is something that is sort of bouncing off the edge and running in a circle. And this is clearly something that shouldn't be there if there's no boundary. And there's a macroscopic density of states in these. And some of these peaks, actually, when you look at the numerical eigenstates, are sort of similar. So sometimes you can look at a region and say, oh yeah, this is a spike of edge states.
Okay.
But it's not always clear. And one of the things is that the states in the flat band are of compact support. And so you can get a clear picture of what they are doing. And that doesn't really change when you add the boundary. You kill some of them at the edge, but the ones that remain are perfectly fine.
Okay.
So,
thank you. If there are no other questions.
Probably that says the flat band is the least hyperbolic of the whole thing.
Okay. If there are no other questions, let us thank Alicia again. Thank you.